I'll be talking to you guys about self-play reinforcement learning. So in particular, I'll be looking at a high-level overview of AlphaGo and its sort of high-level algorithm and how it sort of worked, as well as talking a bit about sort of other information related to that. Yeah, so first I'll talk about some just a little bit of history, really abridged history of some of this stuff. I'll talk about some of the algorithm in more detail. I'll talk about some of the stuff that I applied it to. So that'll be mostly Connect 4, and I'll show an example of that somewhere. And I'll talk about some of the implementation and the results, and I guess any lessons that I've sort of learned from that. Yeah, I guess at any time, if you want to like ask a question, just ask. I'll probably pause a couple of times during the talk to just ask that. But if you want to jump in either in the chat or speaking, I'll try and get to you at an appropriate time. Cool. Okay, so self-play learning has actually been around for like basically as long as sort of modern computers. So one of the first examples was by Arthur Samuel in the 1950s, where he applied some of these self-play kind of really early self-play games to the game of checkers. It used some really early tree search algorithms, including like alpha beta pruning, and actually managed to get some decent results after quite a bit of testing. Backgammon in the 1990s was another big one. This was one of the ones where one of the first real results of using neural networks to get high-level play in a game. So Gero Tesoro, who worked at IBM, yeah, had a neural network that played against itself and actually managed to get to quite high level of play. So one of the biggest ones in sort of recent history was chess, where IBM again, with its Deep Blue computer, managed to beat world champion Garry Kasparov in like a set of 7 games. And that was seen as like a really big thing. So Deep Blue used mainly like a lot of very deep trees and like a bunch of like hard-coded algorithms and tricks that were sort of developed by the programmers, who are also quite good chess players, in order to sort of help the computer play chess by basically simulating heaps and heaps of moves going very, very deep. So what happened recently was that Go has also sort of fallen under the sort of the onslaught of AIs, I guess. And that was actually quite a surprise. A lot of people didn't think that Go would be sort of conquered in the same way, especially that like Go is a more complicated game than chess is. Chess has got like about 30 moves per player. Maybe Go can have up to like over 300. So branching strategies don't work as well. So yeah, that was done by DeepMind, Google's DeepMind, and they used AlphaGo, which I'll talk about through this talk. So first, we'll just talk a little bit about reinforcement learning in general. So reinforcement learning is distinct from supervised or unsupervised learning. In supervised learning, you've generally got a set of objects and you want to put a label on them, or you want to get some sort of value. You've got a set of objects, a set of labels. You can train a neural network or whatever and get some sort of model for it. In unsupervised learning, you've got a set of objects. You want to group them together, like you want to cluster them or something. Reinforcement learning is quite different from this. So you've basically got an agent and an environment. Those are the two most important parts. And the agent is attempting to maximize its score from the environment, whatever that may be. So it could be like an agent in a maze. and it wants to get out of the maze as fast as possible. It might be a self-driving car, and it wants to like not hit pedestrians, and that's its reward. Or it could be a game like chess or Go or Connect 4. So in this case, the environment is the rules of the game and the other player. And in this case, I guess it can be even more complicated than some of the previous examples of like mazes, because like the environment changes depending on what the opponent does. It's not as predictable. Cool. So that's a really brief overview of reinforcement learning. Just set the stage. I'll talk about an algorithm that is quite elementary in reinforcement learning. It's not the point of this talk, but I'll just quickly go over it. Yeah, there'll be a couple of equations in this talk, but hopefully nothing too bad, and you can just sort of glaze over them if you want. So Q-learning is like a really sort of good method for starting with any sort of reinforcement learning problem. It attempts to find the quality, hence Q, of a particular action at a particular state. So you get the sort of state action pairs, QSA, and you want to see how good an action is. So here's the update rule over here. Essentially what this is saying is that in Q-learning, you want to choose the best action for a particular move. And it does this by choosing, it's an iterative algorithm. So it updates the old value of Q based on the reward it gets and some sort of expected future value. And it just keeps iterating over this. Don't worry too much about it. I've mainly just used it as an example to sort of compare it to my simulations with the tree-based stuff. But it's generally pretty good for a lot of stuff. Like it works like well on like Atari games and stuff like that. You can learn to play them pretty well, but not so well again in two-player games like, let's say, Connect 4. Okay. Now AlphaGo. AlphaGo is pretty cool, pretty recent. Started 2016. A couple of iterations. AlphaGo, AlphaGo 0 and AlphaZero. I'll mostly be talking about AlphaGo 0 and AlphaZero in this talk. So sometimes there'll be sort of different implementations. Most of the time we'll be talking about stuff in the last two. Because these ones sort of didn't use any sort of game knowledge of Go, like didn't use any human knowledge of Go at all. They went from scratch, which is pretty cool. Made by DeepMind, as I said, and is essentially just Monte Carlo tree search plus neural networks. Both of these things which have been around for a while. So neural networks have been around since like the 50s, 60s, quite a while. Been getting pretty popular pretty recently. Monte Carlo tree search is a bit older, about 2005. But yeah, have also been used quite a bit in gameplay, especially games like Go. So basically the big sort of breakthrough was basically combining them in this in a really synergistic fashion that worked out surprisingly well. And it's sort of surprising that it took so long in a way. So the neural networks and the Monte Carlo trees reinforce each other. The trees increase the power and the training of the neural networks. And the neural networks help the trees search, and these sort of reinforce each other positively. And so eventually, with enough computational power, you get some real high levels of play. Any questions so far? Cool. I'll continue. Cool. So I'll talk about Monte Carlo tree search, which is basically one half of the sort of AlphaGo recipe. So basically, it's a tree search algorithm. So it constructs a tree of moves, attempts to play through them, and then attempts to choose the best one, essentially. So it's made up of a couple of steps. It does this a bunch of times, so m times. I think AlphaGo used 1,600 simulations for each move. So it selects a move to simulate, then it expands it and scores it, sees how good it is and backs it up, and then it plays the move. So I'll go over these in more detail, but you can see a nice little diagram over here. You've got two Go pieces over here. I took this from the AlphaGo paper. There's a couple of different moves that black can make, and selects a move. Yeah, I'll talk about that now. So this has got a little bit of math in it, but hopefully you can shout out if you want more queries about it. So this uses the polynomial upper confidence bound tree algorithm, or PUCT. So essentially what this does, it's not too complicated really. All it does is like, you've got a bunch of different moves that you can take. It could be chess, could be Go, doesn't really matter. So you want to choose one that effectively is a good move, which is this Q term, and also is something that you haven't explored so much before, which is this U term. So this Q term is the quality of the state and the action, while the U is a sort of like unexploredness factor of it. We'll talk about Q in the next slide, I think. But U is sort of set as this. And as I said, it's a term to force exploration of moves. So N is the number of moves that have been played from a particular action. Number of times the action has been played from a particular state. Well, this is the sum of all moves. So essentially, the less times this move has been played, the lower this denominator, and therefore the greater this entire term is. So essentially, the less moves you play, the higher this term is, and the more you sort of play that move in the future, sort of make sure that all moves are explored well enough. You've also got these constants. There's a constant C term, and there's this prior probability of how this is being calculated. I'll talk about that again later. Was there any questions about that? That can be a little bit tricky.
Yeah, I have a question.
Yeah.
What is the sum in the numerator summing over?
It's the sum of all the moves that have been done from that particular state. So it's a sum. The B is the sum of, if it's like Go and you've got 360 moves available to you, it'll check out how many times all the other moves have been played.
Okay, so you're summing over all actions.
Yeah,
apart from the one we're considering.
Yeah, so it's the sum
or
of
including the one.
Yeah, it's including it, but it's probably not
okay.
going to be part of it. It's just the sum of moves from that particular state. Yeah.
Great, thank you.
Yeah, no worries. Any other questions?
Ruben, sorry.
Yeah.
I guess this probably is like a question related to the slides before, in terms of before the selection. Understand that you have like different moves options, and do you kind of like hard code or like set that up first before you go into the selection phase?
Like what?
So like
what the
how does
possibilities
the how does like the Monte Carlo simulation know like what the moves are to search for the next one?
So I guess you sort of have to give it sort of an action space, and so you have to say these are the possible moves that it can have. It doesn't have to have any sort of meaning, but the way I did it was just give it a vector of like for Connect 4, it's like 7 different actions you can do. And it just picks one of those. And if it doesn't have any context, it just sort of picks one at random.
Yeah.
So it doesn't have any context at this, at all really. It's not playing the game directly, but yeah,
cool.
Just another parameter. Yep, no worries. Any other questions? Cool. I'll continue then. So once we've selected a move, and this keeps going down until it hits a move that it hasn't selected yet. So it does this and then simulates the move, and then it keeps on simulating into the future. So it recursively does this until it hits a move that it hasn't actually evaluated. Okay, then it needs to actually play the move to see what it does, essentially. So you can see that in this diagram over here. So we're at this stage over here, and we expand this move, with white is then moving here, and we're now in this board position. So this node is now being associated with this particular state. What we then need to do is we need to score this move. So we need to see how good the algorithm thinks that this move is. If this ends the game, like you've won, or you've lost, or you've had a draw, it's quite easy. You just use that as the value of the move. Most of the time, that's not going to happen, though. So you've got to somehow score the move for an unfinished game, which is actually quite difficult. And I guess is where AlphaGo kind of really innovates. So it gets this value. AlphaGo uses a neural network. Previous versions used random simulations of moves from it. But in AlphaGo, a neural network looks at this particular board position and then outputs a value. And that value can then be used to sort of score that particular move. Once it's scored, this moves the value all the way back up the neural network. So you've got this value here, and it goes back all the nodes up above it. So all the moves have been have another piece of data to tell how good the moves below it is. So it basically takes the average of the moves below it. It's pretty simple. It just takes an unweighted average. So for this particular move, it's got these two values and just takes an average of those. And this gets done recursively back up to the root node. So I can see how good the values are for all the subnodes. So if you get good scores on a particular move, that increases the value and increases the value of Q, which means that that move will probably be played more in the future. Finally, you need to choose how to play the move. So then you've done this simulation like 500 times. You've got a nice tree. You've actually got to play the move that you've simulated. Generally, this is done in sort of two separate ways, or they're related, but depending on what position you are in. So if you're playing seriously and you want to choose the best move possible, you'll choose the node with the highest number of subnodes. So the move that's been played the most. So remember from before, the selection had a quality component. The move with the highest quality would generally be played the most. And so you basically choose that move. So if there's 3 moves here, this move's been played the most, got the highest number of subnodes. And so the one on the left will be played almost all the time. On the other hand, a lot of the time you need to actually explore the kind of scenarios and explore the game, see what moves are good. So you want to like actually not play what you think is the best to make sure that you're not sort of leaving moves on the table. This was done in the training part of the neural network. So in this case, you sort of take a, you just choose proportional to how many nodes there are. So there's 5 nodes here, 2 nodes here, 2 nodes here. So if you're sort of training the neural network at the start, and you're just generating games to self-play, this might be played 2 nights at a time. This might be played 2 nights at a time as well. But it'll generally prefer moves that has been played more and have had higher quality. Yeah, any questions on that so far? It's most of the Monte Carlo tree stuff. It's probably the hardest part of this presentation. So ask any questions if you want.
If possible, on previous slide, if you move, please.
Which one?
Yeah, probably this one.
Yeah.
You said that, as far as I understand, it's a so-called black-white tree. So one level is played by one player and another layer is played by another player.
Yes.
So as far as I remember, at least in chess game, when we propagate scores from the bottom levels to higher levels, it's like minimum and maximum alternatively, what we are doing here. But you're saying here the score is averaging, which confuses me a little bit.
Yeah, no, I agree. I've been a little bit, that's very true. On each term, what I did is I just sort of took the negative of everything. So if it was black, I had that, and if it was white, I took the negative of it. So it is essentially min-max. But yeah, that's absolutely true. I just didn't want to get into too much detail. But yeah, you choose the maximum of whatever that particular player thinks is best. So from the perspective of, you know, the white player, choose the move that is its highest value, which is the same as a min-max tree. Does that answer the question?
Yeah, perfect. Thank you very much. Thank you.
Yeah, that was a very good question. I was wondering if someone would pick up on that. Anything else? Cool. Yeah, so that's the algorithm, but there's still a bunch of stuff that is sort of unknown. So there's the value of the unfinished games. There's the prior probabilities that wasn't a selection term, and these need to be calculated. So you can do this via like hard coding. So you can sort of have, in this situation, we think it's this good to do this. Or you can do some sort of like random play out, both of which have been used. AlphaGo was, I guess, probably the first one to go full hardcore into the neural networks and basically say, do all of these things by neural networks and train it all. So essentially what it does, it plays a lot of games against itself using this tree network, and then uses the move probabilities and whoever won the game to train the neural network to train these particular scores. And once it trains these scores, it can get better at, they can get more accurate values. And therefore the following tree-based stuff is going to be better. And so it sort of positive feedback loop improves both of them. And so you get some really, really good play. Any questions?
Yeah, so what are the move probabilities?
The prior probabilities PSA or? Sorry. The move probabilities in this bottom, yes. So that's when I was talking about how it actually chooses the move, it gets the tree and it goes, okay, there's 5 nodes here. So the move probability is 5 knights. The move probability here is 2 knights, and this is 2 knights because of the number of nodes. But okay, so even so it's the prior probabilities will correspond to how much what the distribution is of the nodes. There's an equation later on that shows that the actual loss function, but it's related to the number of nodes in subtree.
Yeah, okay. So I guess my follow-up question then is the number of nodes in the subtree, or the number of times you visit a node, is dependent on those prior probabilities, right?
Yes.
And we're estimating those prior probabilities from the number of times you visit the node.
Yes.
Do you have convergence issues there, or?
It's actually surprisingly quite stable, which is, I guess, the trees. So it's an iterative process, but it's quite stable, and it generally sort of empirically kind of works and converges to something that does seem to play better. So I haven't really noticed anything like that. You can choose random weights and it goes pretty well. I haven't looked at anything too far into it, but compared to like Q learning, it was quite stable.
Yeah. Okay.
Yeah, the tree network sort of, I think, stabilizes the whole thing, and so the kind of recursion doesn't get too bad, I guess. But yeah, that can definitely happen a lot in reinforcement learning, but seems to be okay in this.
Thanks.
Yeah. Cool. Yeah, so I first tried this out in Tic Tac Toe. It was just sort of like a ground zero. You all know what it is. You got to get 3 of your token in a row. You can place it anywhere. So that was kind of, didn't really work as a sort of test because it was too simple, and the tree search algorithm could basically get it immediately. So then I went to Connect 4. So some of you might not be familiar with it, but it's a 6x7 game board. 2 players alternate putting tokens, their own colored tokens, to the top of the kind of play area, and it falls down into the lowest unoccupied space. And the aim is to connect 4. So get 4 of the same color in a line, which could be horizontally, vertically, or diagonally. I'll show you a picture of it. So this is a picture of a Connect 4 board. So you put the tokens into the top and they fall down to the bottom by gravity. And you want to get 4 in a row. So you can see in this diagram, the red player has 1 because they managed to get 4 red tokens in a row. So why choose Connect 4? It's pretty simple, but it's not too simple. It's not like Tic Tac Toe. It's not trivial. It's not trivial. So you can sort of do it with sort of like reasonable computational requirements. Unlike, let's say, Go, which I think Google spent like millions of dollars training. So a small action space for only 7 moves compared to like 30 in chess or like 300 in Go. So it's simple. It's easier to program. Technically, it's a solved game. I didn't actually look too much about this. I didn't try and compare it to like the solved sort of probabilities or whatever. So player 1 can technically always win. Yeah. What I managed to get to didn't manage to get to that level of play, but it got decently well. So as a segue to sort of break up the presentation, I'll show an example of it. Hopefully this will work. Cool. Can you guys see like a PyCharm window, like a terminal?
Yep.
Cool. Yeah, I'll just get this started and hopefully this works. So this is an example of 2 agents playing each other. So in this one, player 1 was an agent that is trained for about 1 day with a 6-layer deep neural network. While player 2 was trained for 5 days with a 15-layer deep neural network. So player 2 is stronger, but has sort of been handicapped by the fact that it's playing second, and playing first is quite a big advantage. You can notice that there's a sort of strong bias towards the middle column. That's quite common. So they've learned that the middle column is quite powerful because it can sort of reach both sides of the board directly from it. It's being played at a little bit of a delay. So there's about 3 seconds of delay added into the model. So they'd be playing faster if they could. But yeah. So yeah, so the X's are player 1, which is the weaker model, and the zeros are player 2, which is the stronger model. And we'll see how they go. Currently, they're doing 400 simulations of each move before they actually play. So the M was the value of 400. So yeah, they can get decently far into a tree, but nowhere like can solve the entire game. So there's still a lot of work being done by the neural networks. Any questions while we sort of view this? Yeah, I've got the code. It's in my GitHub repo. Some of it's quite nice. Some of it isn't. The actual Monte Carlo tree stuff is not too bad. I can share it later in the talk. The training stuff used a bunch of multiprocessing stuff, and that got kind of hairy. But yeah, it's... So we're sort of getting to the end game of the simulation. I've noticed that on longer games, as high-level games, games go longer as players are better able to predict moves. Okay, so we can see that player 2 has won. So the stronger player that has played second won by forcing it, by forcing a win. You'll see that a lot of the time in Connect 4. You'll sort of force your players to play moves so that you can get your Connect 4 and it'll sort of inexorable win. Yeah, any questions about that? Yeah, I've tried to play it myself. I pretty much always lose. I have won against the strongest player, but it beats me, which is basically my main goal when I tried to code all of this up. Yeah, and the game, the agents are playing close to what they think is sort of the perfect move. So there's a little bit of randomness, but not much, essentially. Cool. Is there any more questions? Cool. Oops. Yeah, so that code you just saw was written in PyTorch and Python. So we use Torch for the neural networks and Python for implementing the tree algorithm. Because of the high computational requirements, I processed games in parallel. So we had one update process, which trained the neural network, and a bunch of multiple self-played processes, which played games to so that the neural network could train from. So this was trained on the cloud with the K80 GPU and 8 CPU cores. So to do this, we had to sort of have the neural network. So that was done by a 2D convolutional neural network. Had a kernel size of 3 and 2 different heads, the policy head and the value head. The policy head was the prior probability of the move, so how basically how good it thinks a particular move is, or how likely it thinks a particular move is from a particular player, and a value head. So given a state, how much it thinks is going to win from a state. So I started with a 6-layer convolutional neural network at the start, which was enough to span the board, but eventually moved to a 15-layer one, as I found that after a certain time, the 6-layer one stopped improving. I did end up having some dropout layers, which seemed to improve performance, but just pretty uncommon in reinforcement learning, I found, but they seem to work, so I just kind of used it. This is the loss function that I used, and it's the one that AlphaGo used. So the loss function was the sum of the mean squared error of the actual game winner and the predicted game winner, and the cross entropy loss of the move probabilities and the prior move probabilities. So it attempts to sort of make sure that the the value of the winner is as close to as possible as who actually won, and that it attempts to match the prior probabilities from the neural network to the ones that were developed from after the neural network has sort of, after the Monte Carlo tree search has sort of played out its moves. So the neural network basically attempts to sort of match what the tree algorithm has done. And so it gets better at evaluating that. Any questions on that?
I've got one if it's right.
Yeah, go for it.
Do you mind just giving a high-level view of just the convolutional neural network? Because I've done a lot with computer vision. Are the dimensions of the top layer, like the input features, just the board? And then if there's many layers, normally in a video analytics application, the dimensions reduce as you go down. Is that the same here, or do the dimensions kind of stay fixed? How can you have 15 layers then is kind of what I'm trying to understand.
Yeah, okay. So the original input one, it had 3 layers. One was, I think, player 1's position. I think the second one was like player 2 positions. And I think player 3, or the third layer was like the empty positions. So we sort of separated those out into 3 separate channels. Then it sort of, I think I used like 128 channels and just basically kept that constant until like right at the end. I didn't really have a particular great reason for that. It was basically what AlphaGo did. So I kind of copied it. But yeah, there was just sort of no real reduction of channels as it went on.
And even if the filters stay the same, or the channels, the actual size, like the dimension of each layer that's being fed to the next one, do you know what that looked like? It was just the same dimensions.
It was the same one over and over again. It had like a channel size of like 3 that was just sort of slowly moved forward. Yeah.
And that kind of gives it vision of this piece, player 1's piece here, looking in a window around itself at the other empty positions and other player positions. And that's kind of what it's learning filters based on. Yes,
it is. So it like looks at the local positions so I can see like, okay, three pieces in a row, that's pretty good odds for my chances of winning. Yeah. Except if there's a piece in the way or whatever. And as the more and more layers go on, it can sort of learn more of the sort of non-local features.
And would making the kernel size like 5 or 7 or something so it can see the whole board, did that, I don't know if you tried it, did that like give it more vision, or did that kind of just murky?
I think I tried like a kernel size of 5 at some point, and then I just moved to 3 since that was what AlphaGo did. There was a lot of things that I just ended up choosing a number for because there was lots of different hyperparameters. So
yeah, cool. It's really cool. Thanks.
Yeah, no worries. Any other questions? Cool. I'll continue then. So this is the training loop that I did. So first I had to generate some initial games and store the positions. So this was just done by completely random weights from each player. And they just played each other and played some like low-level games and stored the positions and who won and all that jazz. That was done like, I don't know, like I played like a 500 or 1,000 initial games or whatever and stored all those states. So I stored all the states in like a big memory queue thing. Then each epoch, so I did this a bunch of times, I trained the neural network on one worker with the memory of the positions so far, while all of the other workers continue playing the self-play games. So they used sort of the best model so far, which I think was still random. So when they finished this end game to self-play, I think I used like 500. It updates the self-play workers to the most latest trained model. And then I evaluated it against a fixed model, basically to see how all the training has been going. So the loop wasn't too bad. Yeah, evaluating a fixed model had some actual complexities. I'll talk about that later. Yeah, essentially all it did is generate a bunch of games, trained itself on those games, and then kept doing that over and over again. And as it went on, it generated high quality games, so it could learn more interesting stuff from the data, and therefore could keep playing keep playing stronger and learning better. So then I tried to sort of evaluate this. So I used the Elo rating system. So this was done for sort of any arbitrary zero sum to play games like chess or Go or Connect 4. And was originally used in chess, named after ARP at Elo. Essentially, all that matters is that a 400-point difference in Elo means that one with 400 more points has got about a 90% chance of winning. So the higher the Elo, the stronger the player. Also, you have to sort of keep sort of an anchor value, because it's all positional. So in this case, I use the random player and set it as an Elo value of 1. Yeah, so these are the results that I got from sort of evaluating the model. So as I said, you got an anchor value of 0 for a random player. Yeah, nothing interesting about that. Q-learning, or deep Q-learning, after about 3 hours, and where it sort of stalled, about 600. So significantly better than random, but not amazing. Didn't really manage to get Q-learning too well, but oh well. This was a fixed player. This was the one move look ahead was a player which I sort of programmed, like pre-programmed with fixed rules. What it did is it just looked at moves and said, can I win from this position in one move? If so, then play that particular move. It also looked at if the enemy player could win by doing a particular move, and if so, it blocked that. So I managed to get decently well, and otherwise it played randomly. So it got 640 Elo, which was better than deep Q learning and significantly better than random, but nothing amazing. And here we go with the actual trained values. So after 1 hour with 6 layers, I got to 870 Elo. After a day, it improved it a decent chunk to 1100. And after 5 days with 15 layers, managed to get it to about 1500. So yeah, so the 15 layer one can beat the 6 layer one about 90% of the time.
What was your Elo, Ruben?
I was tempted to check it, but I thought I'd be discouraged. So I never actually looked it up. I thought about it a lot, but then I decided not to. I think I'd probably be around, if I had to guess, probably around like the 1100, 1200 stuff. I lost most of the time against this really strong one, but against the sort of slightly weaker one, I could still beat it semi-consistently sometimes. Yeah, so compared to stuff like chess or whatever, there's a couple of, I don't know, you can think about some things. So it's got a quite small action space. So each move has got like a 1 in 7 chance of being the correct move, since we've only got 7 possible moves. So that will basically decrease the sort of spread of Elo, because you've got a more likely chance that a random value will be good compared to like chess. It's like not as complicated a game as chess, for example. Also, I found that the games had about 60-70% chance to be won by the first player, for the same agent playing against himself. So having that sort of high first player advantage means that the Elo will also be a bit compressed, but still managed to get quite like decent results after training. And I only stopped because I ran out of GPU credits on Google Cloud. It was still improving by the looks of it. Yeah. So some challenges. Actually evaluating it was, well, before that, any questions about that?
Yeah, I was just wondering, when you talked about how you can select the moves probabilistically or deterministically, right?
Yes.
Depending on whether you're training or just going full try hard mode.
Yeah.
When you're evaluating your your agent, which are you using?
Yes. Yeah. This is tricky. This is one of the trickiest parts of it. So it's not completely one or the other. Like you can sort of do in between. What I ended up using was something that's quite deterministic, but not fully, because if it was fully deterministic, then you would get the same result each time. So there was that, plus there was a little bit of extra randomness sprinkled on top, which I didn't talk about, but sort of in there. And I set that as a value. So it's, if you look at the games, you'll oftentimes see the same games played again, but not all the time. So yeah, it's close to deterministic, but not. This was a time where I just had to choose something and like go with it.
Yeah. So you like manually selecting your like exploration constant or whatever it was from the previous slide.
Yeah, exactly. This was kind of tricky, and it was sort of just winged it until I got something that looked reasonable. But in a game like Connect 4, like it's harder to do because of the low action space. In a game like chess, you've got more reasonable moves. Oftentimes in Connect 4, if you just don't play a particular move, you'll just lose. So yeah. But they're playing close to what they think is optimal, but still enough that it produced different games.
Great.
But yeah,
Thanks.
Very good question. Yeah, so some challenges. So when I evaluate the games, so actually seeing how good it was, you kind of have to sort of you have to do that somehow. Initially, I just used a random player, but then as time goes on, the self-play games get good enough that they beat it almost all the time, and then the evaluation becomes like useless. So then I did the one move look ahead player, and then the same thing happened. So you have to sort of bootstrap it as well. So you have to get like a previously strong opponent and use that as a sort of the evaluation. That was a bit tricky, and just had to sort of stop and start and use it. Different agents as sort of evaluation as time went on while training the games. Ensuring exploration was tricky. Without it, the same moves sort of get played over and over again. So there was a little bit of extra randomness added at the start of each move, where they were like, we're more likely to choose this particular move, just to sort of force it to sort of play more random. And after that, it played a bit better. Overfitting, making sure that you've got a long enough big enough set of data to sort of train your model, enough games that you've played already. Otherwise, it sort of hones in on those games that are already played and sort of emulates them. So you're going to make sure you've got enough games that have been played and don't train too fast. High computational requirements. So yeah, Google spent like millions of dollars or whatever for AlphaGo. I don't have that. So yeah, it was pretty slow. It took like 5 days to train one of them. Because generating the self-play games take a lot of time, and then you've got to use those to sort of train the neural networks. Hyperparameter tuning, there's too many hyperparameters. I just picked values a lot of the time. Sometimes I did some light tuning, but nothing special. And just PyTorch multiprocessing was just like weird, got weird errors. Stuff to think about if you're doing it yourself. Have a good evaluation framework done from the start. It took me a little bit of time to sort of think about how to best evaluate it and which players to use and what parameters to use. If you've got that sort of set up from the start, it's probably a lot easier, and you don't waste a bunch of time trying to figure out if your agent is actually learning better. Stability stuff, after messing around with Q-learning, learns out how hard it is to sort of get stuff working and prevent positive feedback loops. That's the RL stuff, but luckily it wasn't a big deal in the Monte Carlo tree search stuff. I learned PyTorch. I didn't use that before I did this thing. And it's more effective multiprocessing. Basically, log everything. Yeah. Improvements. I can speed up inference using some extra stuff, like Torch RT or Apex for inference or training. I could use more Torch, and I could hyperparameter tune more. Yeah. Yeah. If I were to improve from here, which component should we look to first? I would probably be using Torch RT. I think it can be up to 3 times faster in inference than the normal Torch code. It's using sort of lower precision numbers. I tried to use it, but was getting a bunch of installation problems and sort of just gave up. But it'd probably be the easiest win. Inference was like the biggest part of the computation. Probably like 90% of the computation was going to inference rather than training. So increasing inference speed would be good. Yeah, if you're interested in this stuff, there's a free reinforcement learning textbook that's very good. Reinforcement Learning and Introduction by Sutton Bardo. And there's also the AlphaGo papers, which go into stuff in more detail and actually quite readable. So you can just Google those. Yeah, does anyone have any more questions? Cool. I think that's that then. We're getting close to 1 o'clock anyway. Kate, do you want to chime in?
No, all good to wrap up. Thanks everyone for coming.
Yeah, cool. Hope you enjoyed the talk. Yeah, hope you learned something. Thanks, guys.